Today's video will define the encapsulation metric of abstraction. Hello, I'm James Helfrich. One of the biggest challenges we have when managing large programs is managing the extreme complexity that characterizes these projects. How do you deal with such complexity? The encapsulation metric of abstraction helps us to characterize this complexity and gives us an avenue by which we can manage it. Software design metrics enable us to better pick between design options and illustrate how we can improve a given design. And there are several different levels of software design metrics. One of them is algorithm metrics, and we're familiar with algorithmic efficiency, this amount of time and space required to complete an action, otherwise known as big O notation. O sub 1, or constant time, is better than O sub n, which is linear. Understandability, how difficult it is for a human to understand a given block in code. And this is critical because we really want the person who's fixing a bug to understand the intent of the code. And understandability helps us to measure that. Malleability is the cost of making changes to a block of code. Inevitably, we have to adapt the code to change the needs of the client. We have to make modifications, add features, and malleability is a measure of the cost of that. We also have modularization metrics. The first of these is cohesion, the degree in which a single function does one thing and one thing only. And then we have coupling, the complexity of the information interchange between functions. Now, we also have encapsulation metrics. The first of these is convenience, how easy it is for the client to use an application. The next is fidelity, the suitability of the class in representing the design concerns. Now notice convenience is about the public methods. Fidelity is about the attributes. But now encapsulation, that is our third design metric. And this is the amount the client needs to know about the implementation details of a class. So let's talk about that. Now, there are several different ways to define abstraction, and each one of these is correct, but they're kind of a different perspective on the problem. So the first is the amount the client needs to know about the implementation details of a class to use it effectively. Ideally, the client would have to know nothing about the implementation details, but this is all about the client's perspective. How much does the client need to know? Another definition, abstraction is the process of shielding users from unnecessarily implementation details. When I get into a car, I don't need to know how many cylinders it has or whether it's fuel injection or carburetor or electric or hybrid or any of those things. I just really want to press the accelerator and have it move forward. And so me as a driver is shielded from those kind of implementation details. Part of abstraction is about effectively using access modifiers, public, private, protected, so the client only needs to understand the convenient public interfaces. So whenever we look at a class diagram, it's the assignment of the access modifiers that is part of the abstraction equation. Abstraction enables the class author to retain control of implementation details, so they could be tuned, modified, or changed without worrying about breaking client code that utilizes the class. When we have an application that is designed without abstraction in mind, everything is highly interconnected. So changing one thing is likely to impact another part of the program. When we use abstraction correctly, it's impossible for the client of a class to know anything about the implementation details of the class, and this gives the class author complete freedom to make changes to the class. Abstraction is the process of reducing complexity of a program by hiding unimportant details from the client. By optimizing on abstraction, program complexity is tucked away into individual classes, each of which can be independently implemented and tested. Applications have an intrinsic level of complexity because we're trying to model complex things in the world. The question is, where does this complexity live? A design with poor abstraction has all the complexity in main, or a small number of functions, each of which is horribly complex and very difficult to understand. When we design with abstraction in mind, we take this complexity, which is inherent to the problem, and we tuck it away so that the overall program does not have to worry about it. Now, there are 4 levels of abstraction, and we strive for complete, but often have it settle for opaque. Now, the best is complete. No implementation details are revealed to the client. There is, air quote, no way the client can know how we implemented things. This is what we strive for, but it's not always possible. Opaque. Unimportant implementation details are revealed to the client in non-mainstream scenarios. Every now and then, our abstraction leaks a little bit. It's likely that the client is not going to leverage these implementation details in their code so that we still have the freedom to make changes. And it's likely the client doesn't have to know these things in order to use the class, but there's still a possibility we're going to have a dependency between different components that we wish to not have. Now, we always want to have complete, but sometimes opaque is really the best we can do because of because of time constraints or technology constraints. Porous. Knowledge of implementation details are very helpful to the client. The client can better utilize the class if they understand how we implement it, which means the client is going to depend upon those implementation details when they use it, which means we're going to have more complexity than we want. This is undesirable. Critical is the worst. The client must deeply understand implementation details. Perhaps the best or maybe worst example of this is a linked list. The client has to know all about the pointer to the next and previous item in order to use the list effectively. Otherwise, then we're going to have a circular list or a broken link or a lost nodes or a bunch of other things. Another bad example of critical abstraction is a C string in C. The client has to know about the null character, otherwise we're going to have a malformed string. Now, clearly, critical and porous is undesirable. Whenever we classify our class as critical or porous, we should look for a better design that's at least opaque and perhaps complete. Now, there are several advantages to designing with abstraction in mind. One of this is reduced development time. When we have a highly complex application, then the developers have to walk very carefully when they make any kind of change. They have to be very cautious, write a lot of test code, and talk to other developers who they rely upon. This slows the process down. Better abstraction means reduced development time. Second, better program comprehensibility. Every human has a limited amount of things they can keep their head at a given moment in time. What we really want to do is reduce the complexity to no more than necessary so that number one, it takes the programmer a smaller amount of time to understand the code they're working on. Number two, it decreases the probability they're going to make a mistake by incorrectly understanding the code. Or number three, it reduces the level of expertise a given person has to have in order to work on the code. For an example, if we have the class author as being the only person that can use the class, then the usability of that class is significantly reduced, and we're not going to be able to use it in other parts of the program as well as we like. Comprehensibility is a good thing. Another advantage is more isolation of changes. This is mostly manifest in the author of the class being able to make optimizations such as performance or understandability or malleability without having to worry about the rest of the program having to change. If you have one class that's used by 100 clients, clearly we don't want to have to look at the code implemented by the 100 clients in order to verify that our change worked. And finally is more stable code. Code with a high level of abstraction tends to be easier to test. The more we can test code, the more we can offer quality assurances. We can learn more about abstraction in the abstraction chapter of the software design textbook.